All right, let's dive into one of the biggest, most mind-bending mysteries in all of science. It's this simple fact. Our universe seems to follow two completely different, totally contradictory sets of rules. So how is it possible that reality itself seems to be, well, broken?
Yeah, you heard that right. This is the question that literally keeps physicists up at night. How can the universe follow two completely different playbooks at the exact same time? To even begin to unpack this, we've got to go back and look at two theories that just changed everything.
So in the 20th century, physics gave us these two incredible ways to describe the universe. On one hand, you've got Einstein's general relativity. That's the rulebook for everything big. And on the other, you have quantum mechanics, the playbook for the super, super tiny. Now here's the kicker. They both work perfectly, like unbelievably well. But there's a problem, and it's a huge one. Okay, so first up, let's talk about the world of the very large, Einstein's curved universe. To really get a handle on the cosmos, the epic dance of planets, stars, and whole galaxies, we have to start with the master himself, Albert Einstein. For the longest time, everyone just accepted Newton's idea of gravity. It was this simple force, right? Pulling things together. But science, well, it never stops moving. In 1905, Einstein comes along with his theory of special relativity and shows that time isn't constant. It can actually slow down. Mind-blowing. So then he spends the next 10 years wrestling with this even bigger problem. Where does gravity fit in? And what he came up with? Well, it was an absolute masterpiece.
So here's the brilliant part. Einstein's big idea was that the gravitational field isn't something in space. It is space. He imagined that space and time are woven together into this fabric, kind of like a giant trampoline. And massive things, like planets and stars, they bend and curve this fabric. That curve? That's what we feel as gravity. So it's not some mysterious force pulling you down. You're just following the curve in space-time created by the Earth. It's beautiful.
And the thing is, this theory just works. It works beautifully. It nails the orbits of planets and stars. It explains the vast dance of galaxies. It even predicted that light itself could be bent by gravity, and it told us about black holes way before we ever had the technology to actually find one. It's just stunningly accurate.
Okay, so that's the big stuff. Now let's zoom in, and I mean way in. We're going from the cosmic scale all the way down to the fundamental particles that make up, well, everything. Get ready, because we're entering the strange quantum world. So, quantum mechanics. If general relativity is this elegant, predictable waltz, then quantum mechanics is like chaotic, free-form jazz. It's the theory that explains the completely bizarre and counterintuitive rules for the atomic and subatomic world. And trust me, these rules are nothing like the ones we're used to. The discoveries here just kept getting weirder. It started around 1900, when Max Planck figured out that energy isn't continuous. It comes in these little packets called quanta. Then, a little later, Niels Bohr realized electrons don't just circle an atom. They make these quantum leaps, literally disappearing from one spot and reappearing in another without traveling in between. And then Werner Heisenberg comes along and drops the biggest bombshell. Maybe particles don't even exist in a specific place until we actually observe them. What?
And just to give you a sense of scale, we're talking impossibly small. You start with an atom. You zoom into the nucleus inside. Then you zoom into the protons and neutrons that make up the nucleus, and you can keep going. You get to quarks and gluons, the fundamental bits. This tiny pixelated world, that's the realm of quantum mechanics.
So, there you have it. A universe divided. We've got these two amazing theories, one for the macro, one for the micro, and both of them have passed every single test we've thrown at them. So, what happens when these two worlds meet? That's where things get messy.
Okay, so taken on their own, both theories are just ridiculously accurate. But the moment you try to bring them together, they completely contradict each other. Think about the center of a black hole. You have an immense amount of mass, that's general relativity's territory, crushed into an infinitely small point, that's quantum mechanics turf. When you try to use both sets of equations there, they just break. They spit out nonsense. They fundamentally disagree.
And this is the heart of the disagreement. General relativity says the universe is curved, continuous, and smooth, kind of like a flowing river. But quantum mechanics says, no, the universe is flat, granular, and jumpy, more like it's made of tiny individual pixels or grains of sand. So which is it? Is reality a smooth flowing river, or is it a pixelated image? It can't be both.
So where does that leave us? Well, this is the next chapter, the quest for unification. Physicists aren't just shrugging their shoulders. No way.
The sharpest minds on the planet are on a quest to find a single, unified theory of nature that can bring these two warring ideas together. Yeah, there's an entire field of physics working on this. It's called quantum gravity. And the whole point is to resolve these paradoxes, to find that one master theory that works for everything, from quarks to quasars, and finally give us a single coherent picture of how the universe really works. And there are a few different ideas out there, a few contenders for this theory of everything, but one of the top ones, a really fascinating one, is called loop quantum gravity. You'll often see it called LQG. And the ideas coming out of LQG are, well, they're mind-blowing. It suggests that space isn't continuous. It's actually made of tiny, indivisible grains or loops, like atoms of space itself. And time? It doesn't flow smoothly either. It has its own rhythm, ticking along for every single process. But maybe the craziest idea is that the Big Bang wasn't a beginning at all. It might have been a big bounce from a whole other universe that collapsed and then rebounded into ours. Just wow.
So, let's bring this back home. What does all this mean for us, right here, right now? We're talking curved space, quantum leaps, big bounces. This isn't just about math. These ideas completely change how we think about reality. And if reality is so different from what we thought, what does that make us? What's our place in this cosmos?
There's a physicist named Carlo Rovelli, one of the pioneers of LQG, and he has this amazing way of putting it. He says, even a rock, which most of us would think of as being very much a thing, is really an event. Think about that. This new physics tells us the universe isn't made of things, it's made of processes. A rock isn't just sitting there, it's an event happening, a slow dance of atoms through time.
And you know what? That's what we are too. We aren't just observers looking at the universe from the outside. We are in it. We are part of this story, made from the exact same atoms as the stars, governed by the same quantum weirdness. We're a piece of the cosmos that has woken up.
And that leads to one last really deep question. If everything we are, our brains, our thoughts, our choices, if all of that is just another physical process, another event governed by the laws of nature, then are we actually free? Are our decisions really ours, or are they just the inevitable result of all the quantum events that came before? You see, the search for the laws of the universe, it always leads back to trying to understand ourselves, and that is a journey that's always worth taking.